So very warm welcome to Professor Luca Guzzardi from the University of Milan. He will talk today about a topic that is very much of interest for the research team. His talk is titled "The Needing Others' Work, Collaboration as an Epistemic Need, and Modern Astrophysics." So thank you very much, Luca. I leave it all to you. Thank you.
Oh, no, thank you very much for this invitation and also the opportunity to share some ideas with you, with your group. Well, I will not say much about paradoxes and metaphor of time in this talk. I will say something about how we, and most of all, why we adopt certain strategies to observe the universe, and to be sure, the early universe, since observing far also means to observe far in the past, into the past. Well, excuse me, I cannot progress. Okay, now I can. Well, I will mostly speak about one strategy which is very usual to us, which is obvious to us, which is collaboration. When we do science today, we do this collaboratively, and this seems a little bit obvious, but it's not obvious at all. Particularly, it's not obvious why we select a collaborative mode of research. Usually, collaboration in science is considered as a social behavior that can be implemented into the epistemic structure as an efficient way to solve certain epistemic tasks, to reach certain goals, such as, for example, to run a large experiment at the CERN, to analyze huge amounts of data in practically every domain of science, to cope with the goals of a project as large as the Human Genome Project, coming to biosciences, for example. And there is a standard account, in fact, of why researchers tend to collaborate and why the group size has generally grown throughout the past century. This standard account is mostly due to Kitcher's the advancement of science. According to Kitcher, we collaborate when we think this is an optimal strategy to attain a certain goal. So typically, we have a certain finite amount of energy energy means everything what you want, time, funds, personal skills, groups, and so on. And you have to invest that finite amount of resources in order to obtain a certain quantity of knowledge at some cost. And when you think that the costs are, or the energy is better invested if the costs are distributed, so if the cost of reaching some knowledge is less, of reaching some knowledge together is less than the cost of reaching that same knowledge alone, then you tend to collaborate. This is, of course, an oversimplification, and Kitcher tries in his book also to make things difficult and make the view wider and richer. But I think also in this very basic form, it contains a very broad and also a sound idea that is simply this: collaboration is primarily division of intellectual labor. We could do something alone, but it's more cost effective for us it's more convenient doing the same thing, the same research together. Well, this picture of collaboration has been very influential in the past 20 years or so. It has been important and helped very much clarify how scientific programs actually advance in reality, not just as pieces of theory, but like actual science. And it also gave room to the social components of the scientific inquiry. It's based on the idea that the epistemic goal on the one hand and the social behavior of the other hand are two conceptually independent things, but the social may, and usually this is the case, influence the epistemic process, whereas the epistemic process has poor influence onto the social aspects. Now, today I want to try to another proposal to invert this idea, this conception, and I will ask if there are cases in which the epistemic structure in the first line does influence the social behavior. If there are cases in which, in particular, collaborative social behavior is needed, not because cost effectiveness, but is needed because of epistemic requirements that I call epistemic constraints. So my answer is yes, and I will give two examples of this idea that I call epistemically constrained collaboration. And this is why I choose this theme here, because it involves the EHT project that first imaged the shadow of the event horizon of a black hole in 2019. And my second example would be very recent astrophysics, the multi-messenger astrophysics that studies the cosmos combining signals different in nature. So this is my piece on the history of astrophysics, a very recent history. But before beginning with the EHT collaboration, let me also clarify one point. Collaboration, the word collaboration in science has often a formal usage. A research project is said to be a collaboration because people cooperate or different institutions cooperate, and collaboration is used in this as a concept, as a formal concept like this. So I can speak, for example, of the EHT collaboration or the EHT consortium with the same meaning. I will use collaboration, the term collaboration, rather conceptually instead, to refer to a certain working mode that involves joint action by any number of individuals. So when I speak of collaboration, I do not intend in the first line this formal usage, a particular consortium or a particular formal usage. I mean the concept of working together in view of a certain goal. And I will use implicitly or explicitly this notion of collaboration. Collaborative research means every approach that aims to achieve a result through operations performed by any number of individual contributors symmetrically joined together. This requirement of symmetry can be expressed in this fancy manner. In order that you collaborate with me, I must collaborate with you. It's somewhat important for me. It means that collaboration is more than collective knowledge. So if I read a book by Sylvia and then I write down my own paper or my own book, this is collective knowledge. Even if Sylvia and me have some sort of idea exchanges, but there are levels of collaboration. Okay, if I participate in psychological experiments and people and scientists scan my brain and so on, it's hard to say, yes, I'm collaborating in this experiment. I'm a subject of this experiment. It's a little bit different. Well, okay, there are looser and tighter forms or more standardized forms of collaboration. I will not speak very much on this. I will not say any word about this, but just to be clear, there are levels of collaboration. For collaboration in this talk, I mean collaborative research as every approach that aims to achieve a certain result and in a symmetrical manner. Now, what about the EHT project and why is it crucial for me? I think that all of you are familiar or maybe remember this image on the left. On April 10, 2019, the EHT consortium announced to have obtained, in the press release, the first image of a black hole using Event Horizon Telescope observations of the center of the galaxy M87. More precisely, what they imaged was the shadow of the event horizon of a supermassive black hole, and behind this there are one or a couple of important concepts. First of all, what is the event horizon of a black hole? This is the boundary within which no direct message except for gravitation can escape from that black hole. And more importantly, in 2000, Falke and others predicted that a distant observer could image such an object, but under appropriate conditions. And these conditions involve using a technique called very long baseline interferometry. I will come back to this, associated with sub-millimeter astronomy, or as it has been actually done with millimeter radio astronomy. Under these conditions, an observer could detect the dark shadow cast by the event horizon because of the strong gravitational bending of photons that are gravitating around the black hole. So it's not exactly that we see the event horizon of the black hole. We see a broader area with in its interior there is also the event horizon and the black hole itself. Now, what do we need to see such a beast? Well, first of all, of course, we need good candidates. We need black holes. Most of all, we need to know where black holes can be, because black holes are black, so we cannot see them. We just we have theoretical models. We know where they probably are, and we can sense, we can detect their gravity, and we can detect, according to Falke and others, also what's going around the black hole. Second, according to Falke and others, we need the LBI, close sub-millimeter astronomy or millimeter radio astronomy. So, about the good candidates. According to our theories and observational evidence of something called active galactic nuclei, so active galaxies, we expect that a supermassive black hole lies in the centers of practically every galaxy. But as I told you, we need supermassive, we need to know where supermassive black holes are, where we could find them, in which galaxy, which must be relatively near to us, because otherwise the space that we can see is so narrow that we cannot see anything really. For such a thing, we have good candidates, in fact, two at least, as far as we know today. The first one is supermassive black hole Sagittarius A star, which is the center of our own galaxy, the Milky Way, just 26,000 light years from here. And the second one is the supermassive black hole at M87 star, the center of M87 galaxy that we actually image, which is positioned at the fantastic distance of 53 million light years from here. But the good news is that we can get such an image. In both cases, however, the central black hole shadow can only be imaged with a particular technique called very long baseline interferometry. Why? Well, because as I told you, the area that we can see that the black hole occupy in our fields of view is so narrow that we need something very big to image such a beast. And to understand this concept, we need the idea of what is resolution. Well, what is a telescope? A telescope is just an instrument that, according to the definition given by Federico Cesi in 1611 to Galilei, the telescope is an instrument that brings closer distant objects. And to bring closer distant objects, of course, you have to magnify the object, but this is in general not enough. Let's look at the image in this slide here. On the left side, you see just a bright spot on a background, on a dark background. It's just a white spot. It's just a bright spot. We don't know any other things about it. On the right side, we see the same object, but this is not a bright spot anymore. There are two spots, which are two stars, and note that the instruments that imaged that object are two different instruments, have a comparable magnifying power. However, the one on the left side is ground-based as the observatory in Las Campanas, and the second one is the Hubble Space Telescope. The two images are not different in magnification. You see the same proportions. What is very different here is the resolution of the two images, is the resolving power of the two instruments. So imagine a telescope with high magnifying power but poor resolution. It will magnify atmospheric distortions as well, as in the case of Las Campanas. And a good example are cheap digital cameras in this kind of device, in our or in my, at least, in my smartphone. What is the resolution? Resolution is the degree to which the fine details in an image are separated and detected or seen. It is governed by this equation. And in these terms is an angle. It's the angle formed by your point of view and the two or more fine details you want to distinguish. It is the smallest angle under which it is possible to see objects as separated. It depends, it's directly proportional to the wavelength and inversely proportional to the aperture, that is how large is your objective, or the objective of your camera, your eye, for example, your pupil, for example. So resolution is a feature of the detection of any kind of electromagnetic waves. It applies to any instrument capable of detecting electromagnetic waves. Your eye, your optical telescope, but also infrared telescopes, microwaves telescopes, or radio telescopes. But note, there are two things here very important. The one is that it is, as I said, it is directly proportional to the wavelength and inversely proportional to the aperture of the instruments. So if we are at the same distance from an object, we can see better if we use, first of all, a telescope with large aperture, because we minimize the angle. And second, if we observe electromagnetic waves with short wavelength, it's easier to resolve visible light than radio waves, because radio waves are 1,000 until a million or 1,000 times larger than visible light. But we do, of course, we do radio astronomy for many different reasons. We observe the sky also in radio waves radiation. And again, the resolution equation gives us the reason why we tend to build radio telescopes or telescope of every kind with very crazy apertures, with big apertures, such as those in these two photographs, Effelsberg on the upper side in Germany, and lower side is I don't remember the name. It's in China, and it's the largest radio telescope, single dish radio telescopes we have just right now. However, there is of course a bad news, which is, well, there are physical limitations to the size of the apertures we can build. And in the case of the supermassive black hole at M87 star, Falke's calculations showed that the aperture needed was comparable, more or less comparable with the size of the Earth. So we need an aperture as large, a telescope, a radio telescope as large as the Earth diameter for such an observation. With Sagittarius star, A star, things were better, but then there were other problems. For example, too much light or too much interstellar medium that blurred our view. We cannot resolve the resolution concern with a single dish radio telescope, but what we can do is to try to circumvent the problem through another method. And this method is interferometry. What is interferometry? This is a technique that combines signals from the same object, so for example, from one star, to two or more separated telescopes that are calibrated on the same wavelength. Why this is a good news? Because the resolution of an interferometer is more or less equal to the maximum separation of the stations involved, which are, of course, calibrated and synchronized on the same wavelength, and synchronized at the same time of observation. So, for example, imagine to have one station in Munich, where I'm in this moment, and Milan, which is more or less 400 kilometers from here. So you have one station in Munich and one station in Milan. If the two stations are well calibrated and synchronized, and we have an interferometer, so we build an interferometer with such a baseline, this means that the resolution we get is the same as we would have a single dish with a 400 kilometers aperture. I find this really amazing. It's a technique that was employed for the next time, 9021, with visible light, I think. And now we also have very long baseline interferometry, radio interferometry, so with radio waves. So the idea there is that the more the baseline is enlarged, the more the resolution is enhanced. And if we want a radio telescope with good resolution, what we have to do is to build an array and calibrate the radio telescopes, literally worldwide. How could it be possible to image such an object 53 million light years from here through the LBI, through building an interferometer whose baseline is approximately as big as the Earth's surface. Of course, the construction of such an interferometer requires multiple levels of collaboration, for example, in the synchronization calibration phase, in the error analysis, in imaging teams, in the infrastructure, in funding the project itself, in the political concerns or problems that different states or nations hosting the facilities can have, and so on. But I think that, after all, the epistemic level is relatively more important than the other. Not because the other are just fancy, but because the epistemic level is the basis also for the other levels to appear. I try now to express this, what I mean for an epistemic level. What is the epistemic level here? So a certain technological instrument, the LBI, which entails collaboration. You cannot do the LBI without collaborating with others. Why this kind of technological instruments is needed? Because of the features of the object investigated. You want to know about a certain thing about a supermassive black hole. In particular, you want to have an image of a supermassive black hole. But it's happened that you are so far away from a black hole. So you need certain methods of investigation. What is the method of investigation you need? It's a telescope, but it's not a normal telescope. It's an interferometer. Why? Because of the resolution equation that is in a certain sense your constraint. The resolution equation says that your resolution equals wavelength divided for the aperture of your telescope. And the only mean you have to reach a resolution, to reach enough resolution to image such an object, is to collaborate with other people. Okay, of course, these are interconnected aspects. Imagine to be on a spacecraft in the movie such as Interstellar, and you're orbiting the last stable orbit around a gargantuan black hole. In this case, you don't need absolutely epistemically constrained collaboration, or you don't need any kind of collaboration to image the black hole. It's simply there. Why? Because the features of the object investigated, in this case, do not promote a collaborative approach. Your methods of investigation are different. Well, it's okay. other factors, of course, can also be important, and they can strongly suggest to collaborate. But the way things are encapsulated in the equation resolution, or in the resolution equation, leaves no choice to us. We must collaborate. It's not for the shortcomings from economical concerns. It's not for technological limits alone that we collaborate. There are these are also important factors, but they come after the first real factor. If we would be in another situation, we have to collaborate for other reasons, maybe, but not for epistemically important reasons. Okay. It seems that in this case, collaboration may be required in the form of a spatial separation. So one could question, okay, but it's not just collaboration. It's not an epistemic constraint. It's a somewhat geographical or spatial constraint. It depends on the spatial distribution of the stations. So I asked to myself if this is the typical case of every kind of collaboration, every kind of epistemically constrained collaboration, if every kind of epistemically constrained collaboration has to do with spatial separation, and my answer is no. I think there are cases of epistemically constrained collaboration in which spatial separation is not as important as in this case. And my example in this case, and with that I come to my second example, is the multi-messenger astrophysics. This is, I try to go quickly. This is an emergent and rapidly growing area of astrophysics based on the combination of information that we got from different signals. Note that these signals are called messengers. Signals are electromagnetic radiation, neutrinos, cosmic rays, another kind of particle, and gravitational waves. And they are called messengers because what we are interested in is not to study the messengers in themselves, but to study their source through the messenger. The basic idea is that different messengers bring different information about the same source from which they can be released. And this allows or enhances our knowledge about important processes in the universe, such as galaxy formation, early universe, black hole masses and distribution, neutron stars, and supernovae from which neutron stars are born, and so on. We already have a good example of this from 2017. On August 2017, on 17 August 2017, our detectors for gravitational waves detected a signal in the channel gravitational waves, detected a pulse of gravitational waves coming from a certain area of the sky, but gravitational waves detectors have a poor resolving power because of the wavelength of the gravitational waves. Okay, and more or less at the same time, just 1.74 seconds later, the Fermi Space Telescope, which is a gamma ray burst telescope, also captured a signal in the gamma ray, which was compatible compatible with that source that also released the gravitational wave. But in the Fermi case, it's also true that also gamma ray are not that the Fermi at least cannot position exactly the source of the gamma ray. So what did scientists? They distributed an alert to other facilities saying, okay, we have captured that signal. Please not only confirm if there is something in the sky of this kind, but please provide more exact information about the position. And this was made by optical telescopes with which successfully identified the optical counterpart in a certain galaxy. If you look at the image here, the position is more and more becomes more and more precise according to the, with reference to the different messenger that is detected. Another instance was sometimes later on September 22, when a neutrino was captured by the ice cube in the Antarctica, and then another alert was given by other facilities, which checked the signal in the X-ray, gamma rays, optical channels, and then radio waves. And at every stage, you see that our knowledge about the process grew up. So it's not that you simply cross-check an event in order to say, okay, my theory is right, no, my theory is falsified, or something like this. You want to distribute with others, to collaborate with others, because you want to have a precise knowledge of what you are observing. Different messengers, as I said a couple of minutes ago, bring different information and can only be observed by different instruments. Messengers and the instruments we use for detecting them have complementary advantages and limitations. And the multi-messenger astrophysics simply combines advantages to overcome the limitations. But this implies that multiple actors, or facilities in this case, must share symmetrically their individual contribution. They must collaborate according to my notion of collaboration I put forth. So, of course, there is a similarity here with the EHT project. In both cases, collaboration seems to be required and driven by epistemic concerns, not only by costs and burden costs and so on. However, here, as you say, spatial separation is just contingent, I would say. Of course, the facilities are also spatially separated, but this is not the most important thing. The most important thing is that they are capable of detecting one signal or another signal. And we do not have the possibility to build a facility that can detect all these different signals. So contributors are epistemically separated in the sense that each messenger represents a different piece of knowledge we need to know about a certain phenomenon. And then I tried also to explore how this epistemic separation may occur. I will go very quickly on this. I do not elaborate further, but if you want, this is for our question and answer time. Some processes cannot be rightly understood with standalone signals, so we need others' contributions. As I said, for example, gravitational waves provide excellent information about the black hole masses or the neutron star masses that are melting, but they do not provide good information about angular resolution. So the positioning of such signal is practically impossible. But at this point, we can pass on the task to to the astronomers of electromagnetic waves, so radio astronomers or optical light astronomers and so on. Thus, combining several messages maximizes their individual strengths and provide a formidable toolkit. So an article, one of the most important article about multi-messenger astrophysics, providing a formidable toolkit for proving the most dramatic astrophysical events. Other times we have to do with subthreshold events that are maybe significant, but if they are regarded as standalone, then they remain under the threshold of significance. And what we should do is to lower the threshold, but to lower it, we mutually need others' work. There is a fantastic program, I think, called AMON, Astrophysical Multi-Messenger Observatory Network, that combines and seeks to perform a real-time correlation analysis of the high energy signals and so on. It's fantastic. I have it on my own smartphone, and you can also receive gamma ray burst alerts or neutrino alerts, and this is important, I think. This is a typical kind of an alert you receive. This event, neutrino alert, this event has a certain chance to be a neutrino of astrophysical origin, so it may be caused by a supernova, but to identify the source, we need another signal from a different messenger to understand the mechanisms powering the emission. We cannot do it alone. And finally, different messengers have different times of arrival or are released at different times. So it's better for us to involve other facilities, other astronomers to continuously check our data and maybe acquire more knowledge, or also have a feedback on past subthreshold events. But this is little bit complicated, so I can only drop these points. I had something interesting to say, but I think we also my time is practically at the end. So let me try to conclude why I see in multi-messenger astrophysics case of epistemically constrained collaborative research. Well, we expect that there is something out there. We can only know by putting together different contributions, different messengers. And look, the construction of an instrument, even in the electromagnetic domain, is highly dependent of the bandwidth or the wavelength interval we wish to know about, we wish to observe. Or in the case of the multi-messenger astrophysics, on the particular messenger we wish to detect. So we must do multi-messenger astrophysics if we want to know about it. It's similar to the thing with interstellar movie. With my example with the interstellar movie, I take another movie or another series. This is a Star Trek series, a character in the Star Trek series, who is provided with this visor that enables him to see in multi-wavelength optics. So he can experience, he can see infrared from heat, or visible light, or also microwaves and radio waves. but it's not real. We cannot do this. If we would do this, then we could have the possibility at least to go alone and to do alone multi-wavelength astrophysics. But for the time being, our capabilities and our methods constrained us, or are the constraints to do something collaboratively. So since we expect that the object under study has certain features, messengers, sources that release some messenger, and we can only use certain approaches to study it, certain kind of facilities, and we cannot build a visor like that, we select ultimately a collaborative mode of knowledge, not because, or not merely because of economic constraints, but because we want to know something in a definite manner. And I think I can conclude here. So thank you very much for your attention, and I'm curious about your questions and also your feedback, your criticism, and so on.
Thank you very much, Luca. Okay, so are there questions? Yes, Fede.
Hi, can you hear me?
Yeah.
Yeah, thank you very much for your talk. It was very interesting. I had a couple of, let's say, clarification questions. The first one would be about the kind of epistemic constraint you are arguing for. So would you say like that the cases of study make it necessary for there to be a collaboration in order to, let's say, produce knowledge, or maybe they make it convenient? Because I don't know, maybe it's silly, but in principle I can think about someone building its own telescope as big as a planet, you know. So the collaboration comes because a matter of convenience in this case. That would be my first question. And the second one is, in both cases you have talked about collection of empirical data, which will be, I mean, collaboration is required in order to, both in the MMA and in the black hole photo, collaboration is required in order to collect all the empirical data which are needed somehow. But I was thinking if you also thought about cases in which maybe it's not much the collection of empirical data, but rather maybe different theoretical backgrounds that are needed by the collaborating people in order to produce the knowledge. I don't know, maybe no. An example could be, I don't know, the study of the notion of causality in psychology or rather metaphysics and how it's interchanged or stuff like that. Thanks.
Yeah, thank you for both questions. Are very interesting. To the first question, I think they are necessary. So there is a necessity of collaboration. Epistemic constraint, as I see them, in this case, necessitate, are a causal factor in a certain sense for collaboration to appear. Well, you said, okay, but in principle, I can think about a super advanced technology that could build also a telescope with maybe with adaptive optics as big as a planet. Yes and no. So there are probably also physical constraints to what we can do. But even if the answer is yes, as I said, depends on the situation we have. So epistemic constraints are not just theoretical. If we would be, I repeat, if we would be on a spacecraft around a black hole, we don't need, we wouldn't need a kind of collaboration. But since we are in another situation and we have to use a certain equation, then we need to collaborate. Okay, so there are, but you're right, there are multiple aspects on this. I'm elaborating more exact. I gave not much attention to the idea of the epistemic constraint in itself. Otherwise, I would begin with this, and then the time is quickly ended. The second, your second question was collection of empirical data, but also different theoretical backgrounds can let emerge collaboration. Yes, my answer is yes. I agree. Also in physics, we have something like this. Also in multi-messenger physics, astrophysics, we have something like this. The theoretical background of a supernovae explosion is quite different from that of other of a blazar or of a black hole and so on, and of a black hole merger, for example. And if we have more theoretical backgrounds, then we can understand better, and we need to have more backgrounds. So this is a little bit in between collaboration for epistemic constraints and other kinds of collaboration, but
yeah, okay. Thank you. I leave other speakers. Thank you.
Other people want to ask questions? Laura?
So thank you very much. It was really interesting. I have a small clarification question regarding the first part of your talk. And so I found very interesting the point you raised about the symmetry. So the symmetry within the individuals and the people involved interacting in a collaboration. And so my question is, yeah, it's really naive, and I just wanted to know a bit more, how should we understand precisely this kind of symmetry? So does it involve some kind of horizontal relationship? So, and if not, so non-hierarchical relationship, I mean, and if not, what does it require exactly? So perhaps that all members in a group are somehow necessary. Yeah, thank you.
well, thank you. Very difficult question. It's not naive. It's very difficult. I mean, I asked to myself the same thing, and I asked it many times. And I didn't find a good answer up to this point. I mean, it's clear that there must be this idea that in order that I collaborate with you, you have to collaborate with me. We have to be conscious of this collaboration, okay? But then, what does it mean then? Is it horizontal? No, there are hierarchies, and you can have collaboration also with hierarchies. It's collaboration is often hierarchical. So you are collaborating in your group, but there is a hierarchy in your group, and this is this happens every time in science. I mean, the EHT consortium has senior scientists like Heino Falke or Shep or others who have the complete control of the group, and at other levels there are PhDs, there are professors, there are researchers, pure researchers that have a responsibility of one or two groups and so on. But my point is that within each group, also hierarchically expressed, there must be a certain symmetry. Okay, I cannot express up to this point this more clearly. I'm not able for the time being. So sorry, it's a good point. I must do more about it, but good spotted.
Are there other questions? Okay, so I have one. So what do you think is so special to multi-messenger astrophysics with regard to your thesis, let's say? So what does really makes it special? Because if you think of the definition you provide here, precisely in the slide that you're presenting, we can say that with the Manhattan Project and the birth of big science, collaboration is vital. I mean, and also think of the development of high energy physics. I mean, today we have experiments run at LHC that clearly lead to results precisely because there is such a type of collaboration. And so it's clear that the physics under analysis is different from the one that you investigated in your talk.
Yeah. Okay.
Why did you select then multi-messenger astrophysics rather than examples taken? I mean, it's replete of examples.
Okay.
Taken
Well,
from high energy physics.
Well, the reason was contingent. Why I have selected multi-messenger astrophysics. The first reason was that I had a criticism one time, and the criticism invited me to search for other cases. And I thought that one interesting cases could be multi-messenger astrophysics, because it is also strongly interdisciplinary in a sense. Okay. But then if I have to go deep into the reason now that I have now, I think that multi-messenger astrophysics, there is this tension. It's true that the EHT is based on spatially separated stations, but for the multi-messenger astrophysics, it's not like this. Okay, and in the big experiments as the LHT, the problem as regarding collaboration is much more blurred. I mean, I cannot separate these aspects completely. Okay, but maybe it's just for me. LHC is also one. I thought about considering LHC, but I couldn't find really a good kind of interpretation of of what they're going on. That was going on there. So it's. But maybe it's just a matter of time.
I mean, we can maybe continue the discussion also in presence. I mean, it's not necessary
Yeah,
to
yeah.
tell all details here. I was just wondering if you
Well, there is to
take
be
into account or not, and you know, or for example, I could make another example with regard to current astrophysics and cosmology. So, for example, we have missions that should provide information, okay, either regarding the geometry of the universe or I don't know, the so to speak, the network that in principle connects, if any, our galaxies and so on and so forth. The point is that in all these type of collaborations, and they are huge collaborations indeed, you have at least two sources from which you take the information. One is from you know, the tools that you send to space, and so from telescopes that you use in outer space. And let's say you compare what you obtain from that tool with what you obtain from Earth. So you combine basically the data that you collect from one source with the other. Of course, you need huge collaborations, and this collaboration, let's say, or this forced collaboration is needed for many reasons. Among them, and that's why I mentioned LHC before, is the big data handling problem that needs to be solved. So it's a constraint. Okay, so it's what forces you to have many collaborators coming from different places in the world, working on different branches of the same discipline, and having different expertise in order to select the relevant data for your analysis. So this is the also another reason to be taken into account in the discourse when we want to talk about collaboration today, I think, in current science, in current physics or astrophysics. So again, but of course, if it's I mean, you presented a work in progress, so I'm not saying this to criticize you. I would like just to either know if you already thought about other case studies maybe to be included, and therefore also to incorporate them in this.
I have in mind. Other case studies. I didn't mind this case study that you are reporting to me. So I will surely it's interesting because there is also in this I see here also a good potential of for developing further this idea that of epistemically constrained collaboration. So you are saying that in this case we are probing the geometry of the universe through multiple contributions, and we have to do so. Not only, it's not like James Webb Telescope. This is very interesting, but James Webb Telescope is one telescope at that time that provides us information about exoplanets, for example, or other kinds of, but it's just one. I mean,
I'm referring basically also to the collaborations that basically study dark energy and dark matter. So this is
I didn't thought about it, but it's potentially I see it as a good example. So thank you very much, Sylvia, for this. It's just interesting. Well, there is another reason for why I selected astrophysics and astronomy, because since ancient times, at least ancient maybe not, but just to consider how you can construct the path of a comet. This was an important problem in the 18th century astronomy. And for that time, you couldn't do this alone. You needed the contributions from many other astronomers. So this was my departure point, because I was involved with this big project about Roger Boscovich, an astronomer and scientist who contributed very much to the physics and science of the 18th century. And he was also involved with the discovery of the planet Uranus in 1783, and also involved comets and so on. And for astronomy, it has always been important for observatories, it was always been important to be connected with other observatories, because data could be shared, and so they could provide new information and new knowledge. And this is the reason why I have to do with astronomy primarily. But what you told me is very promising. Thank you.
You're welcome. Are there other questions or clarification questions? No? Okay, so we can thank our speaker again. Thank you, Luca, for having presented today. Thank you all for having been here, and we should reconvene for the next seminar on the 17th of March. Thank you.
Bye, thank you very much. Bye-bye.
Bye-bye, bye all.